Assalamu alaikum and welcome back again. So in this lecture we are going to discuss the classification of the signals, and based on this classification we can say that we can classify them into the following uh, 5 categories, that is continuous time versus the discrete time signals, even and odd signals, periodic and aperiodic, also called non-periodic signals, and deterministic and random signals, and the final category is energy signals and the power signals. So to recap, let's start again. What is a signal? So signals and systems are ubiquitous to uh, all the major fields of the electrical engineering, namely telecommunications. We use them there, we use in the control, in the signal processing, power, electrical power engineering, and so on. Engineers must model two distinct physical phenomena, that is physical systems and physical signals. Physical systems are modeled by mathematical equation, whereas physical systems are modeled by mathematical functions. The example of the physical system is shown here. This is an electrical system, a circuit where we have inductor, resistor, and capacitor. So this circuit can be modeled by for this mathematical equation, right? So this one models this circuit, whereas the examples of the function can be, for example, we take the voltage applied to the speaker in a radio, or the other example can be the temperature uh, signal whose value varies with the time. For example, at the daytime, you understand it will start increasing and decreasing, and at night time normally have some wee hours of the night we have very minimum temperature, and then again it starts increasing, so it's also a function of the time. Examples of the signal include, for example, by nature we can say they can be electrical signals. So electrical signal, you understand, are voltages and currents. They can be acoustic signals or the sound signals, right, such as speech signal, or they can be mechanical in nature, for example, velocity of a car, or they can also be a video signal like intensity of a pixel, variation over time. We can also have others, for example, biological signals, and so on. So this we have done in the previously. This is just the recap, so I will just go quickly through them. So what is a signal? Then we say a signal is a function of one or more variable that convey some information on the nature of physical phenomena, right? So based on this definition, we can say a signal can be function of one independent variable, or it can be function of more than one independent variable. So if a signal is function of one independent variable, then we call it a one-dimensional signal. Whereas if it is function of two independent variables such as image, in that case we can say image means black and white image or grayscale image, right? So in case of grayscale image or black and white image, the independent variables are the positions, pixel positions x and y. So in that case we call it a two-dimensional signal, whereas it can also be multi-dimensional, more than two-dimensional, right? For example, the video signal is a function of x, y, pixel positions and time. So it is a function of 3 dimensions. Similarly, we can say color images. So we are just adding the dimension, right? Mathematically, signals are represented by as a function of independent variable. So for example, here we have f of t. So f of t signifies that f is function of the time. Similarly, f of w tells that in this case the independent variable will be w or the frequency. So f of t is basically time domain signal. F of w is basically a frequency domain signal. So independent variables tells us whether it's a time domain, frequency domain, or any other domain like we have here ixy, which shows that there are two independent variable, one is x and one is y. So this is basically an image signal. So here xy signifies its position, and it says that this is basically a space domain signal. So in this particular course of the signals and system, we will be dealing with one-dimensional signal. That means the independent variable will be either time or it will be frequency. For instance, an RC circuit signal may represent voltage across the capacitor or the current flowing in the resistor. There's always associated system with the generation of the signal, right? So we can say that signals are basically generated by the system, they are received by the system, they are transmitted by the system. Okay, for example, we have a sound signal. So sound signal is basically generated by the vocal tract, lung, etc. The process of speech signal usually relies on the use of our ears and auditory pathway in our brain. This system is biological in nature. Okay. So now we come to the main topic of our today's lecture, that is classification of the signal. So in brief, we can say that, or we can summarize that signals can be classified based on the independent variable. If we have one independent variable, we say it's a one-dimensional signal, and if we have more than one independent, then we say it's a multi-dimensional signal. Similarly, if the independent variable is time, then we say it's a time domain signal, and if the independent variable is frequency, then we say the frequency domain signal. So in this particular case, we'll be uh, dealing with those signals that have time as independent variable, which we call them time domain signal, and frequency as the independent variable, which we call them a frequency domain signal. So first, let's classify the signals into different classes. So the first class is continuous time signals versus the discrete time signal. So it's very clear that if the independent variable is continuous, then we say it's and time, continuous and time, then we say it's a continuous time signal. So continuous time signal is represented by x of t as here. So here t signifies that it's a time domain signal, and also it says that it is a continuous time signal because t has continuous values. Examples of the continuous time signals can be sound waves, can be electrical signals such as current and voltage. You understand that the electrical signals are basically two, current and voltage. So the electric power signal we receive, that is 220 volt. So that also varies with time, and time is also continuous. So we say it's an electrical power signal which you get at our homes is an example of continuous time signal. The discrete time signal is the one where independent variable is time, but it has discrete values. That is, it is defined only for a discrete instant of time or discrete interval of time. So it is represented by x of n. If you compare the two notations, for the continuous time case, the independent variable is t, and we use the parenthesis, right? And for the case of discrete time signal, the independent variable is n, and we use the square bracket. So if there is square bracket, that means it is a discrete time signal, whereas for the case of parenthesis, it is continuous time signal. Discrete time signal may occur uh, in nature, denoting a discrete, denoting some phenomena in time, or we can also obtain the discrete time signal by discretizing the continuous time signal, or we can also say by sampling the continuous time signal we can obtain the discrete time signal, right? So how it is done, then we say x of n equals to uh, x of t, and if I take the discrete values, so how can I take the discrete value? I can say, okay, I write x n t s, and the small t is replaced with n and ts, where n is an integer and ts is the sampling period. So after how long you should take those samples, that is your sampling uh, period. Okay, the reciprocal of the sampling period is the sampling frequency. So if we take the example of this, we can say that because nowadays we have a digitized telephony system, right? And our speech signal is analog or continuous time signal. Now to use that system, we have to uh, make our speech signal discrete time. So how we make it discrete? We take its samples at some sampling frequency. Normally for the telephone quality speech we use 8k hertz sampling frequency. That means we take 8,000 samples per second to uh, discretize the speech signal. So here is the example of the continuous time versus the discrete time signal. So shown on the left, this one is the continuous time signal or CT signal, whereas shown on the right, this one is discrete time signal. As I mentioned earlier, that we can obtain the discrete time signal by sampling the continuous time signal. So here is an example of how it is done. Shown on the left side is example of continuous time signal, while the one on the right is its discrete time version. So you can easily know, you understand how it is obtained. So if I sample at some sampling period ts, then I will obtain the values of this signal at some discrete interval of time. So this is how we obtain the discrete time signal from the continuous time signal. Remember that the signal shown on the right is not a digital signal. It's right, because it is discrete in time, but as far as its amplitude values are concerned, they are still uh, real, right? They are not quantized. So this is a discrete in time, that you understand that if we look at this, the signal on the right, it has, you see on the values along the t-axis, they are continuous. Also values along this axis, right, which we call them value of x of t. So values of x of t are also continuous, right? So the digitized signal will be the one that you discretize it using the time axis, and also you quantize it along the values, then we call it a digital signal, right? So this is still in terms of uh, time, it is a discrete time signal, but in terms of values of the x, it is x of t has the real values. The second classification of the signals is into even signals and odd signals. A signal x of t or x of n, you understand that for even and odd they can be both, like that means continuous time signal can be even and discrete time signal can also be even, right? So for even signal, we say a signal is said to be even if x of minus t equals to x of t, right? For the continuous time case, what does that mean? It means if the signal is symmetrical about the zero time, that means for positive values of t and for negative values of t, x of t has same value, then we say it's a symmetrical about the vertical axis, and it is called the uh, even signal, right? So even signal can be continuous time and even signal can be a discrete time signal, right? Similarly, a signal x of t or x of n is referred to as an odd signal if x of minus t equals to x of minus x of t, right? And for the case of discrete time signal, x of minus n equals to minus x of n for all n values, right? So what does that mean? That means that if you move from towards positive side, right, the values of the signal will be anti-symmetric to what you have from 0 towards negative side. To make it clear, so we see the following examples. These are examples for the even and odd signals, and I hope it will help you clearing your concept, right? So the signal shown here, the signal is basically example of even signal. If you look at this one, this zero axis, if either you move positive side, that means if you move this side, or if you move away from the zero, that is towards negative side, you see that the signal is same. That means it's symmetrical about this axis, zero axis, if you move this way or that way. So that means it will not affect its values. So that means it is an example of the even signal. Okay, now for the case of the odd signal, this is the example of the odd signal, right? So here you understand that from at 0 it has the maximum value, right? So if you move away from 0, that is from 0 towards the positive values of the t, the signal is decreasing, but it has positive amplitude, right? Now if you move from 0 towards the negative side, you see that it has a negative amplitude, right? So that means this signal is anti-symmetric. From 0 towards t, it has positive values, and from 0 towards negative t, it has negative values. So that means this signal is an example of the odd signal, right? It can also be like from 0 towards positive t, it has a, for example, negative value, and from 0 towards negative t, it has positive values, but they are same. So we say again that signal will also be called odd signal, right? For example, we can plot a signal here. Okay, for example, these are the axes, and for example we have something like this, and it has something like this, right? So for example, this is the minus a side point, and this is the plus a side. So again, this signal will be called the odd signal, because you understand from 0 towards positive t, this is your t side. So from 0 towards positive t, it has negative values, and from 0 towards the negative t, it has positive values. So it is basically anti-symmetric. So when this is anti-symmetric, that means this is an odd signal. So that means for this we can say that x of minus t equals to minus x of t, right? X of minus t equals to minus x of t. Or in other words, we can say there will be reversal in sign. So if you are move from positive to negative, there will be reversal in the sign, whereas in case of the even signal, there will be no reversal, or it will be same. So again, if we look at the bottom row, in the bottom row we have plotted a discrete time signal. So if you look at this signal, you can easily say that it has same value from 0 to positive n, or from 0 to negative n. So this is an example of the even signal. Similarly, this one shown at the bottom right is an example of the odd signal, because at 0 this is 0, at 1 this is 1, so at minus 1 sorry, not at 1 it is 1, at 1 it is 1 by 2, at 2 it is 1 by 2, at 3 it is 1 by 2, and so on. This continues in this direction, and 3 dot indicates basically that this signal is continued one, right? So again, so on this side it has negative values, and on this side it has a positive value. So that means from 0, if you move towards positive, the values of the signal are positive half, and if you move from 0 towards the negative side, the values are minus half. So that means this is an example of the odd signal, because they are anti-symmetric. Okay, that you understand. It can also be like from 0 towards positive side it has negative value, and from 0 towards negative side it has positive value. So that signal will also be called the odd signal, right? So this is how we represent the how we define the even and odd signal. So let's jump to the mathematics behind it, and let's see how we can split a signal or express a signal in terms of its even and odd parts, right? So we can split a signal into even and odd parts, and for example we have a continuous time signal x of t, so we can say x of t basically equals to x even of t plus x odd of t. Or if you have a discrete time signal, then we can express it also in terms of its even and odd parts. So x even so x of n equals to x even of n plus x odd of n. So let's say this is our equation 1. Now by definition we know that for the even case, x even of t, right? So x of even of, if this is even, then x e of minus t will be equal to x e of t. And similarly for the odd case, x o of minus t will be equal to minus x of t, because you understand this is symmetrical about the vertical axis and this is anti-symmetric, so that's why we put a negative sign here, right? Now if we replace t by minus t in equation 1, right? We're doing these calculations for the continuous time case. Similar arguments apply to the discrete time case also. So for the case of the continuous time, we take this example, okay, this equation, and we say we replace t with minus t. So that means we will get x of minus t, right? X of minus t will be equal to x e1 of minus t, right? This equation plus x odd of minus t, right? So because we know x e1 of minus t equals to x e1 of t, so we can write x of minus t equals to x e1 of t. And because we know that x o of minus t equals to x of minus x o of t, so that means we can say that x of minus t equals to x e1 of t minus x o of t. So this is our equation 2. Now to find the value for x e1 of t, we add equation 1, which is this part, right? Because we are just talking about the continuous case. So we say, okay, so this is our equation 1 and this is our equation 2. So adding them will result into, because if we add them, you see x e1 of t and it's also x e1 of t. So if we add them, it will become 2x e1 of t. And again, this x o of t and this is x minus x o of t. So that means minus and plus, they will stand cancelled. So that means x x of t plus x of minus t equals to 2x of et. So if we shift 2 to this side of the equation, it will be x, we will get x value for the x e1 of t, and value for x e1 of t will be equal to 1 by 2 x of t plus x of minus t, right? So that means to find the even part of any continuous time signal, what we do, we will if we are going to do it graphically, so we just draw the signal x of t, and then we draw the signal x of minus t, and then we just sum them and scale them by a factor of 1 by 2. So we get the even part of that signal, right? Similarly, subtracting equation 1 from subtracting equation 2 from equation 1 will result into getting the value for the odd part of the signal, and this is equal to xo of t, right? And that's equal to scale by 1 by 2, similar to what we had for the even part, xt minus x of minus t, right? So again, to find the odd part of any signal, we can do it graphically by plotting the original signal x of t and taking the reflection of x of t, which is x of minus t, and subtracting the x of reflected part from the original signal and scaling it by 1 by 2 will result into the odd part, right? So similarly, similar arguments or logic apply to find the even and odd parts for the discrete time case, right? Now to get a better idea, let's take an example to find the even and odd parts, right? So again, I will say that same logic apply to the finding the even and odd parts for the discrete time case. We are now considering only the continuous time case, right? So this is a signal that you understand, it's exponentially decaying signal because power of e is like minus, so it will be decaying if we move away from 0 towards positive side. So that means at positive infinity it will be touching somewhere 0. Okay, so this is exponentially decaying signal multiplied by the cos of t. So that's our what we may call it exponentially decaying cosine function, right, or cos function, right? Now the first step to find the even or odd part is that we replace t by minus t to get x of minus t. So to get x of minus t, we replace t by minus t. So we get x of minus t equals to e power 2t cos of t. You understand that cos is basically even function, right? So the value of cos, right, our cosine wave from 0 towards infinity is same as 0 towards negative infinity. So you might know that cos is basically an even signal, whereas sine is odd signal, because if you move from 0 toward right, so it has positive, whereas if you look at the waveform, you find that from 0 towards negative side it will have the reciprocal or antisymmetric thing what we have for 0 to positive side. Okay, you can observe it by yourself. So that's why cos of minus t equals to cos of t, right? So we have the formula for finding the even component or part of the signal. So that is equal to half x of t plus x of minus t. So that means by putting the values, we get half is okay, same x of t is your this original signal, and then you say okay, plus x of minus t, which is this one, right? So taking cos of t common, and we know that basically 1 by 2 into e power t plus e power minus t is basically cos hyperbolic function. So that's cos hyperbolic of t, because we have here 2t, so it will be cos hyperbolic of 2t times the cost cos, right, cos function. So this is the even part. Okay, now to find the odd part, you understand, we'll subtract them. So by subtracting, we get minus sine hyperbolic 2t cos of t, right? So you understand basically the equation for the sine of hyperbolic function is basically 1 by 2 e power t minus e power minus t, right? So this will result into sine hyperbolic 2t into cos of t. So this is how, using the equation, we can find the even and odd parts of a signal. So let's take an example to find the even and odd parts using graphical method, right? So for example, we have a signal, right, that won't be that accurate, but I hope you understand it. This is just to give you the rough idea how we can do. So for example, this is our signal, right, and this is 0, and from 0 up to this is 1, and this is 2. Okay, and the amplitude is for example 1, right? So this is our x of t, and this is t. Okay, so just one pulse exists for this brief duration. Okay, so this signal, as you understand, that's 0 beyond this side, and it's also 0 beyond the 2. Okay, now the first step is to find x of minus t. So you understand this is x of t, so x of minus t will be its reflection, right? So that means we can say x of minus t will be something like this. Okay, this is your x of minus t. So this is 0, and this is minus 1, and this is minus 2. Okay, so how you find the even part? That's quite straightforward. Even part you can find by just adding the x of t with x of minus t and scaling it by a factor of For example, this peak amplitude is 1. Okay, so how you find the E1? The E1 is just defined as the sum of the, so we have T here. You understand, reflection is just you put a mirror here and you get the image on the of this signal this side. Again, if you put a mirror here, you get this side here, right? So x of minus t, because if you put a mirror here and you take the image of this side, because this side all are zero, so you get this thing. Again, you put here in this direction, that the image of this will be formed here, so that's what you get. Okay, now for the case of even signal, we just sum the two and we scale it by a factor of 1/2. So if I sum these two, you understand the corresponding values will be added. So if you look at this side, all are zeros. Okay, you understand. When all are zeros, so up to here you see the signal is also 0, so zeros here plus zeros here, that will result into 0. Whereas on this side these are all zeros and this is 1, so right, that's a increasing signal, ramp signal, right? So if I add this 0 with this, you understand, anything added with the this will result into this, or simply we can say 0 is the additive identity, right? So x plus 0 equals to x, that you understand. So that means from 0 up to infinity, addition of this and this will result into again the same thing, but because we need to scale it by a factor of 2, so that means previously it's 1, but because now you understand that we need to scale it by a factor of 1/2, so that means now the peak amplitude will be 1/2. Okay, again we add this because point by point addition, so that means you see this signal is 0 all from around, right? From 0 up to infinity, this will be 0, whereas this signal is non-zero from 0 up to 2. So if we add them, we'll get something like this. Okay, and again because it has amplitude of 1, peak amplitude is 1, and we have to scale it by a factor of 1/2, so that means now we get the even part will be something like this, right? So this is the even part of the resulting signal, right? So the even part of the signal, this signal x of t will be something like this. That's not very accurate, but I hope it will give you just the idea how we can do it, right? I did it because so that you know how the variables are added. I'm sure you're very good at adding the constant, but this and I hope you will know how we add the variables, right? But if you do it an example similar to what I did here, then I hope you will have better understanding of how we can add the variables. Simply we can say signals are variables, right? So they are variables, or we can, in a mathematical way, if we say, then we can say they are function of some independent variable. So I hope those things are clear to you. Again, if we just go for the odd part, so you understand for the case of odd, the odd part of the signal is given by the original signal minus the time reflected version of that and scaled by 1/2. So if I take the, you understand this is x of minus t, so if you look at the formula says this is equal to x odd equals to, right, x odd of t equals to 1/2, right, 1/2 into x of t, right, minus the reflected version of x of t, right? That's x of t. Okay, right? So that is t. I hope you understand. Okay, so if you look at here, you have the original signal, you have x of t, and you also have x of minus t, because here you need minus x of minus t, so that means to make it minus I will just flip it, right? So it will be something like so this will be the right, so this is your minus x of minus t, right? And this is your t. So if I add this and this, I will get and scale it by a factor of 1/2, so I will get the odd part. Okay, so here we go. And because if you understand, right, if I add this, because this side is all zeros, so again it will result into the same thing, right? But it will be scaled by a factor of 1/2. So now I can say at this point I have minus 1/2, something like this, right? That's minus 1/2, and here I have 1/2, right? So if you understand that x of t plus minus x of minus t, right? So I have minus x of minus t, this thing, and plus x of t. So because x of t is 0 all around here, so I get the same thing, that is this, and I will get this thing. So this will be something like this, right? So this is your odd sig part of this signal x of ot, right? This is signal. So I hope that it clears your concept, and I hope you understand how we can get the even and odd parts, or even and odd components of a signal, right? So in the previous slide we did the same thing using the formula, and now we did it graphically, right? So I hope now it will be very clear to you how we are going to do it, right? So I think for this lecture that's all. This is just repetition, a type of recap, because we have done this, I think, right? So in more detail we have done it, but that's just the recap type thing. And we will have live session, right? So I hope you have received your timetable. So during the live session you can ask the questions, and I want you to go through all the slides which I have explained you here. Go to think and ponder over each and every point, and if you have any question you can ask, and I will be very glad if I receive so many questions, because by questioning you can develop your concepts develop your concepts, and you will have very clear concepts. So if you ask questions, right, so you can ask any type of question, like in the class I normally say you can ask as basic questions as possible, right? I mean, that's a very low level question you can ask. So I appreciate those things, and I think it's an opportunity for you, because you have your lectures in advance, so you can sit at home, you can read, you can listen to them, you can read the slides, and maybe I think that will be a better option than normally in the class we have, because in the class if you skip something, that's all. But here you have the recording things, you have the slides, so you can go anytime, right? And you can think over them, you can use them over and over again, so that will give you better, I think that's a better one. So take this an opportunity, and uh, try to develop your interest. So that's all for today. In the coming lecture we'll talk about the other classifications, right? So That's all for today. Thanks.